Thank you very much for joining. Today's webinar is about how climate models work. I think we're going to have a really good discussion. A lot of y'all know that physical risk modeling is very important, certainly for just the compliance component of what everyone's doing with SB 261 or CSRD. To comply with IFRS S2 guidelines, you need to understand your physical risk exposure. And it's also where a lot of the value comes in because people understand it. It's very tangible. Everybody saw the wildfires 6 weeks ago in LA. People saw the news of the devastating floods in Kentucky this week that have killed over 14 people, that have forced 300,000 people to lose power. That creates a really strong emotional story that people understand, but it's also a really big business story. And that is the point of these guidelines is to say investors and regulators and you as the business operators want to understand what your exposure is. And so we're going to talk about physical risk modeling, how it normally works, kind of the science behind it. And so this is what we're going to talk about. Actually, let's fix this. There we go. So we're going to talk a little bit about who we are and why we're talking about this, what's expected. So from a regulation perspective, what sort of physical risk modeling you need to do. We'll give a few examples of a few companies and sort of risk modeling that they put forward and how they report on this. We'll talk a little bit about Beehive, and then we're going to turn it over and I'm going to interview my co-founder, Dr. Ed Knudsen, is going to give a short presentation, just like teaching a little bit about how climate risk modeling works, and there'll be plenty of time for questions. So ask questions throughout. We got the chat open. I've got the Q&A open. If anything interesting comes to mind, let's talk about it. So what is expected of you when you talk about climate risk modeling? So in the guidelines of the TCFD, which is what all these regulations are based on, there's a few sections in which you need to talk about what your physical risks are. And specifically, you're going to talk a lot about it in the strategy section, where you're going to talk about what risks have you identified over the short, medium, and long term. You're going to talk about the impact of these risks on your strategy and financial planning, and your resilience of your strategy, specifically including a 2-degree or lower scenario. So what this really is expecting you to do is to begin to understand what is the impact of different physical risks of wildfires or floods or hurricanes or heat waves on my business today. How does that change across the medium or the long term? And how does that change across scenarios? And scenarios means, what if climate change in 10 or 30 years is really bad and there's a lot more warming than we expected? What if it's not so bad and either predictions are off or global policies have aligned so that global warming is minimized? I need to understand this. A few more places where they actually talk about this fairly bluntly, this is also from the TCFD guidelines, it's kind of they define exposure. One of the examples they give is the physical aspects of climate change. And they have this nice line here that the complexity and uncertainty associated with climate change makes it difficult to identify the touch points and timeframes. So the starting point, assess the value chain over a reasonable time frame as it relates to physical risks such as the disruption of operations or destruction of property. So they're really specific about what they want you to do. And the reasoning is pretty clear here that there's a lot of uncertainty. And we'll talk a little bit more about this with Ed, but climate models is not crystal ball future prediction. You're not saying, I know with 100% accuracy that wildfires will occur here. They actually stated here that there's a lot of uncertainty and complexity, and that's why you want to consider scenarios so you can be prepared for this. They dive into this a little bit more. This is from the IFRS, which is sort of what the TCFD has transitioned into, where they talk about where they define physical risks, that they talk about acute risks, as well as what they call chronic physical risks. And acute risks come from events like storm, floods, drought. Like there's a moment a thing is happening, a crazy wildfire is occurring, a crazy flood is happening. And then there's chronic physical risks, which are these longer term shift in patterns. Like what happens if you get 3 inches more of rain in a region over the course of the next 20 years? How does that affect crops for an agriculture company? What happens if there's sea level rise over the next 30 years? How does that affect insurance prices for a real estate company? So how do these more chronic changes affect what's going on here? And there's this nice little chart here. This one's from the EPA, but it's referenced from the TCFD that talks about these acute and chronic physical risks. And it gives some examples over here of all those things. So the increased severity of weather events and the financial impacts like reduced revenue from production capacity, higher costs from negative impacts on workforce, write-offs of existing assets, and so on. So let's talk about a few examples of how this shows up in company TCFD reports. I'm going to pull up 4 examples. We've got Expedia. This one is Workday, HubSpot, and GitLab. So in Expedia, I thought they did an interesting thing here where they talk about their physical risks and they specifically cite the increased severity of extreme weather events. And they tell you about the scenarios that they worked on, how they looked at 41 Expedia locations representing high business importance, and what they looked at: extreme precipitation events, flood risk, coastal flooding. And they talked about the scenario analysis modeling that they did. And there's a few interesting things here where they talk about the weather disruptions that might affect their operations, how their travelers are just demanding safer and more resilient travel options. And they even talk about how it's going to affect financial planning because they now need to figure out how to move their travelers to places that are safer. If everyone wants to go to Bermuda, but Bermuda rains for 20 more days a year than it would have otherwise, that will decrease revenue from Bermuda sales, and they need to be aware of this. So that's how Expedia talks about this. And you can actually see a lot of detail here in their physical risk assessment because of how material this is. You can also look at a company like Workday. Workday is a software HR business, and they, as a fully distributed software HR business, say a little bit less detail than Expedia did. A little blurry here for some reason, but they talk about how the increased frequency and severity of heat events may disrupt the data center operations, and rising mean temperatures affect the supply chain and operations, one in the short term, one in the medium term. So you can see that they also disclose how these physical risks affect the business. You'll see something similar in HubSpot's report. So HubSpot has one of the better reports I've seen on physical risk. Just to point out a couple of things. Some companies I talk to say, we're a software company. The impacts are very light. Like physical risk doesn't matter to us. We can just skip that part. You take a company like HubSpot, which is a cloud software company in the most traditional sense, and they actually talk about having a high likelihood in the short term of supply chain delays due to chronic physical risks, a high likelihood in the short term due to increased operational costs from extreme weather events. And they go into some detail of these impacts, talking about how they're going to need to retrofit their operations and their offices, how there'll be drops in employee productivity. So these become fairly material risks for a company like HubSpot. I'll share one final example and I'll talk a little bit about how the modeling works, and I'll pass it over to Ed. But this is from GitLab. GitLab's interesting because GitLab is a fully distributed software company. So all their employees are remote. They don't have offices. All their data operations are in the cloud, I think via AWS. So they don't even own data centers. So for them, you might say, wow, there's really no risk. Like all our employees are distributed. Sure, a fire is a terrible thing, but it's not, there's nothing we can do about it, and the risk is not ours. But even GitLab, with that context, what they did is they conducted a scenario analysis for 10 key remote member hotspots. They said, where do we have clusters of employee and of senior employees? Because if those clusters are impacted by some sort of disaster, like a fire or a hurricane, and those people are pushed out of their homes or lose power, like it's happening in Kentucky, or are not allowed to work for whatever reason because they got to relocate their entire family to a hotel and the school's closed, so they got to take care of their kids. That does create material business impacts. And partially because it's a business continuity issue, your employees can't work, they can't get the job done, but also partially because it's your job as a employee heavy business that really your whole values giving great employees a good place to work. It's your job to figure out how to keep them safe, how to keep them secure, and how to keep them wanting to work for your business because your business responded faster than a competitor's business in terms of keeping them safe. So I thought even GitLab with a company like that did this work. Now, really quickly on how climate modeling works, and I think GitLab is a good transition here. The reason they looked at 10 key remote member hotspots is because traditionally, physical risk modeling is a very time-intensive and therefore very expensive process. When GitLab worked with their consultant, and they use this large sustainability consultant, folks in the ESG universe probably know well, they paid him quite a bit of money. That consultant said, hey, we need to do a lot of desktop research per region in which we want to do any sort of physical risk report. So every additional region to which you want to understand the risks of will be an additional X amount of money. And so GitLab had to prioritize budget. And instead of looking at the hundreds of zip codes in which they have employees and adding to that where they have AWS data centers or maybe their key customers are located that might disrupt operations, they said, we really got to limit it to just 10. And that's because doing the research for what might wildfire risk be in northern Tennessee, where I have a factory, or in this part of Florida, how will hurricanes change over 30 years if climate change is really bad, and how might that affect my insurance? That is a very time-consuming and expensive process. And so that's one of the things Beehive is built to fix. So this is the Beehive software. Now, traditionally, where you might go do a lot of desktop research here, we basically automate a lot of the climate risk work. I'm just going to show you a couple of things. First of all, you can see a bunch of assets in here right now, offices and data centers. I'll show you employees in a moment. And then you can see the risks and how they change. So this is a risk map of wildfires in the United States. This is flood. This is heat. This is how it changes in the medium or the long term. This is how you might consider it if climate change is really bad or if it's not so bad. And so you automatically get to see all this work. Everything I just did in 4 seconds normally takes a consultant a very, very long time. And many of your options are just doing it one location at a time and maximizing it at 10 or 15, because who can possibly do this for the hundreds of locations in which you might have employees, for example? Well, it's cool here, and it actually becomes very easy to measure risk to employees. And so we're going to do what everyone tells a salesperson never to do, which is a live demo. But I'm basically going to drop into CSV of a bunch of zip codes and a made up number of employees you might have in each zip code. And you'll see if things go well, automatically you get to see risk to all of those employees. And you begin to understand this data and say, where do I have employees who live in high risk areas? What are these risks from? Is it more wildfires or floods? How does that change over time? They populate in the map automatically, and you can really begin to do a lot of this research to say, hey, we really take climate risk seriously. We really understand how our risks change across wildfires, which are not a big deal in Texas, to floods, which now in Houston become a much bigger deal, to heat, which obviously continue to increase in importance. And you can do this for regions all over the world. You could look at the risk maps to India. I didn't put any assets in here. You could do the UK and Ireland, with many more geographies coming soon. So that's a little bit about the push for climate risk modeling, a little bit about how companies might be doing this risk modeling today, and a little bit about how Beehive automates this work. Very last thing, audit trails are always so important because this is an investor-facing document, so you can't just make up a risk score and see what happens. So what's cool here is that you can actually see the reason for our calculation for any one of these risks. So if you want to understand or tell an investor, hey, explain to me why the risk is so high here. Or even better, if you go to a low risk region, explain to me why the risk is so low here, because you're telling me it's not material at all. Well, you want to have an audit trail to say, this is why we think floods won't happen, because in the past 30 years, there have been barely any floods and there's been barely any loss. And here's how that's forecast to change over time. So anyone here who's an investor relations professional, a legal professional, in the finance department, you know that you want to get investor facing documents audited. You know that you can't just put forth information that says, yeah, we're low risk, don't worry about it, because no CFO is going to approve that. So this audit trail is going to help do that. So with that, I'm going to turn over the presentation to my partner here, Dr. Ed Knutson. Ed is a Stanford postdoc who's been doing climate modeling for much of his career, and he'll talk a little bit about how climate models work, where trade-offs happen, and I encourage you to chime in with questions specifically about like how we do these decisions and how we make these trade-offs, because there's no such thing as a perfect crystal ball here. Climate modeling is not about predicting the future exactly, and you saying, you told me there were hurricanes were going to happen in this zip code, but they happen 8 zip codes to the left. That's not what we're doing here, so there's a lot of trade-offs. So Ed, take it away. You're on mute. The classic Zoom webinar faux pas.
Okay, can you see my screen okay?
There we go, you're all set up.
Great. Okay, yes, Adriel said I want to give an overview of how these models work, and my goal here is to improve a mental map of how to think about these models and hopefully prompt some questions or discussion around topics that are of particular interest, such as a particular risk score, et cetera. I've got 5 slides. I want to first start by comparing weather modeling and climate modeling because weather is such a useful reference point that everyone is familiar with. And then I want to go on to talk about what's going into these climate models, what's the community that's developing them, what are the key inputs, what are the key sensitivities to think about when you're evaluating, does this make sense as a modeling result, does it not make sense? And then finally, I want to talk a little bit about the heat risk forecasting application that Adriel just mentioned. What data gets us to those numbers, and what choices do we have to make when creating that workflow? So I'll start with the weather versus climate comparison. On the left are typical numbers from a weather model that you might find on your phone or on your web browser. And on the right are those comparative numbers for climate models. So a typical weather model will run 10 days forward in time at roughly a 10-kilometer resolution. And that means we're getting one temperature data point for every 10 by 10 kilometer square in the US. Climate models, by contrast, typically run 100 years forward in time. And because they run so much longer in time and require so many more physics submodels to be active, the resolution tends to be lower so that we can have sufficient compute to do the entire simulation. So in a climate model, a resolution of 100 kilometers instead of 10 kilometers is typical. So these are coarser data points that we're getting. Weather models typically try to forecast realization. So is it raining at my office from this time to this time? What will there be thunderstorms on this day? Climate models, by comparison, tend to try and forecast statistics. So in this decade, will there be more or less heat waves than in the prior decade? Weather modeling accuracy tends to fall off significantly after this 10-day or 2-week time period. And so, of course, that's why the models are not run for longer. And that accuracy fall off for predicting realizations is inherent in climate modeling. And so that's why we rely on the statistical predictions of these models rather than particular realization predictions. The weather models tend to run for hours on a CPU cluster. So in the US and Europe, a big weather model will update several times a day. And that means the model has to, let's say, take less than 6 hours to complete its 10-day prediction. Climate models, by contrast, can run for weeks or sometimes even months on supercomputers. So at a national lab with many thousands of CPUs working in concert, a machine might work on a single climate simulation for a month or two. That's a very standard practice right now. And finally, it's interesting to note that weather models don't consider a lot of the physics that climate models do. And the reason is that a lot of physics that are important for climate models are more or less static over the time frame that weather models are run. So we don't consider CO2 concentration in the atmosphere for a weather model because it doesn't change meaningfully over a 10-day timeline. But conversely, over a 100-year timeline, this does change. And so we need to account for those effects in doing these statistical predictions within the climate. Same thing is true for ice coverage and other sorts of physical influences on the climate. Okay, so climate models were conceptualized in the 50s and 60s, and they started with single domain physics. And what that means is that we would just do a simulation of the atmosphere, just do a simulation of what's going on in the ocean, and treat that as a standalone prediction. And over time, as we've added more compute capability, the coupled treatment between oceans and atmosphere has really become a standard, and adding more resolution, so getting from hundreds of kilometer resolution to in the best models now 50 kilometers, tens of kilometers resolution, let's say, has been a driver of improvements in these models. And then also adding physics to the models has been one of the big trends in climate modeling. So better radiation modeling, better treatment of cloud physics, cloud interactions with aerosols. Those are some of the key evolutions in this modeling over time. The way these models are set up is by first meshing the Earth's atmosphere and the ocean. So you see the image from Wikipedia here is a very nice visualization of a mesh of the Earth, where we create a mesh in the latitude and longitude coordinates, and then also in the height of the atmosphere for our third dimension, and in the depth of the ocean for our third dimension if we're simulating the ocean. And we set an initial condition, so we have to sort of, from observations or from some random perturbation, create an initial version of every mesh cell's temperature, pressure, et cetera. And then we apply some forcing conditions. And in climate modeling, solar radiation is one of the biggest forcing conditions. And that's affected by the gases in the atmosphere, of course. And then the governing equations for fluid flow, heat transfer, radiation are solved on all of these mesh points. And we typically will advance in 45-minute increments. So sometimes it's 30 minutes, sometimes it's an hour, sometimes it's 2 hours. But this is roughly the time scale at which we get data as we're running forward in time for 100 years. And you can see a single time step from a particular climate run in the lower right here. And this gives you an idea of the resolution of these models. I've regridded this from the native climate model resolution to something that we use for analysis, but it's indicative of the sort of resolution you get from these simulations. And you can see this is a plot of daily max temperature ranging from 40 Fahrenheit to 100 Fahrenheit. And you can see that it's certainly able to capture tremendous spatial dependency, but not at the resolution of some of the weather models that I've talked about. Okay, I think it's interesting and helpful when thinking about these models to understand where they come from and who's working on them. So climate models are primarily developed in government and academia, and there are just a wide variety of code bases that are used to produce these simulations, and an even wider variety of physics submodel code bases and of post-processing tools that are run on the results. You see a map in the upper right here of international groups that also work on climate models. So this in particular are contributors to the CMIP6 modeling effort. And in the US, Jet Propulsion Laboratory, Lawrence Livermore in California, and then some of the atmospheric labs like NCAR and NOAA are very key in this climate modeling effort. A lot of these climate models results are open sourced for government use, for academic use, and for industry use. And I think that gets to the CMIP6 bullet point here. And I'm sure everyone has heard about CMIP and discussions around climate modeling. That's an acronym for Coupled Model Intercomparison Project. And it's just an effort to bring a lot of these global modeling groups together and to learn from all of the different efforts about what's working, what's not working, what do we have high confidence in, what do we have low confidence in. And that effort really fosters an uncertainty estimate. So in the lower right of this slide, I'm showing this canonical plot of global mean average temperature. And this is from the IPCC. You can see this black line in the plot, which is the observed temperature rise. This is just what we measure from 1850 to 2020. And around that is this sort of beige band of simulated temperature rise. And that band represents an uncertainty estimate. And that comes from a variety of sources, but one of the key sources in determining how wide that band is the different results that all of these climate models produce. So when we run 25 different climate models and for the same case and get 25 different answers, that's a key insight into what the uncertainty associated with prediction is. And it is appropriate to think of climate modeling as an ensemble effort because most analyses will ensemble average many climate models to get their answers. And that's, I want to end this slide with a comment that even industry uses these climate modeling results as the gold standard. They're certainly the de facto approach to doing climate modeling, even if you think of corporate studies or corporate interest in this topic. Okay.
And then really quickly there,
Yeah, go
just
ahead.
kind of clarifying question or comment there. I think it kind of gets to the point that these models are not predictors of the future as much as they are like tools to estimate your options, right? Like seeing that because these models aren't ensemble. It's saying, well, this group thinks wildfires might get 30% worse, or maybe we're better. Heat might rise by 30%. This group says 10%. No one really knows. So many factors might affect that. Somebody goes, makes 40 new laws that restricts global emissions. All of a sudden, the number drops. Somebody AI comes out and all of a sudden data centers need a lot more energy. All of a sudden the number increases. So it's not about which one of those is correct. It's about these all seem fairly reasonable. Can we combine them and use that to build some sort of strategy for our business moving forward, right?
Right, right. Like so much of risk analysis, the appropriate lens to have here is probabilistic thinking rather than will X happen or will, rather than this one event is either going to happen or not happen, right?
Mhm.
It's probabilistic outcomes in these models, and especially when you consider an ensemble of the models, and that's the right way to think about interpreting the results. Yeah.
Okay.
The inputs that Beehive has on this web app for risk modeling include which SSP you're considering in a climate model. And SSP stands for Shared Socioeconomic Pathway. That's effectively an emissions forecast. What will emissions look like in the next 100 years, and how will that influence the makeup of the gases in the atmosphere? And the biggest influence this has on climate models is on radiative forcing in the atmosphere. What you're looking at on the right here is a plot from a very standard paper on connecting SSP scenarios to actual gas concentrations in the atmosphere. So you're looking at CO2 concentrations in the top here from zero up through our 2000 era. And you can see this big curve for SSP5. That's the red line that really goes up and to the right. And for other SSPs, this CO2 concentration curve is a lot lower. And so when you're picking an SSP, you're effectively picking what is the concentration of gases in the environment. And the way the model sees that is what is the radiative forcing in the atmosphere due to those gases. So that, and it's also important to be aware, again, on the probabilistic topic, that it may not be that we land on one SSP in particular. It could be, these are all discrete curves, but reality might be a blending of these curves. It might be a little more of this curve for a while, and then a little more of that curve for a while. So there's an inherent uncertainty in the assumptions about these SSPs that is important to be aware of when interpreting results. Other uncertainty sources in these models besides the SSPs are mesh resolution. So an interesting example of this is hurricane prediction. A lot of these global climate models tend to significantly underpredict hurricane frequency relative to what we observe historically. Some of that is due to the low resolution. So hurricanes are inherently strongly convective events. There's a lot of small scale featuring compared to a global length scale. And if we use 100 kilometer by 100 kilometer resolution, we're not going to pick up on all of that behavior well enough, and we'll underpredict hurricane frequency. So those sorts of things happen in the climate models and are worth being aware of. Physics submodels are also an uncertainty. So cloud behavior and cloud aerosol interaction is a very active topic of research in the field and influences model behavior. And then the last thing I want to mention is that as a part of CMIP data gathering, a lot of these climate models will go through verification exercises in which they shock the Earth system with an instantaneous doubling of CO2 and then observe how the Earth's environment responds. So you can kind of do these made up but useful experiments of, if I do this to the Earth system, what happens? And different models show different behavioral curves after a shock like that. So again, it's a comment that the models are very complex. They don't all give the same answers. And that's one of the ways scientists try to improve the models, but it's also important to keep in mind as you're thinking through, okay, how accurate is this? What does this mean? Last thing I want to share is an application of this CMIP6 data to heat risk forecasting. So Adriel just showed you in the web app some of our risk scores. And I want to walk through the chain of events that we use to get there. So I'm going to use the US as our region of interest here. And the first thing we do is take 20 of those CMIP6 simulations that I just talked about for a given SSP and extract temperature and humidity data. And we will concatenate a lot of simulations worth of data together so that we have a lot of data to process and to get the best statistics we can with. And then we'll build on top of the raw temperature and humidity data to get quantities like the number of days above 99 degrees per year in a given location, or the maximum 1 month average, rolling average of daily max temperature. So for example, that quantity would be calculated by stringing all of our daily temperatures together, taking a 1 month rolling window and walking through that data set and recording that 1 month rolling average, and then looking at the entire data set and picking the maximum value. So that's the maximum expected monthly average daily max temperature within the modeling result. And when we think about heat risk, we kind of want an ensemble of these things. So heat risk isn't just one thing. It's not just temperature above this threshold. And it's also a little bit relative. So we've talked a little bit internally about how much there should be a relative component of heat risk and how much there should be an absolute component of heat risk. And we don't want to go too far in either direction. If it's only relative risk, then everywhere in the world will be high risk because everywhere in the world might see a day where the max temperature is 7% above the last month's average temperature. But you don't want to entirely rule out relative risk either, because some locations might not be as prepared for a hot day, or 96 degrees might affect a cold location much more than 100 degrees affects a hot location, right? So these are choices made in thinking about risk that are not set a priori by the climate modeling results. Humidity effects are also very important, right? So we can weight humidity more or less in thinking about how much heat is concerning as a risk factor. What I'm showing on the right here is one of these metrics. On the top, you see the number of 99-degree days per year in the US. Obviously, we get concentrations in the Southwest and through Central California and around Texas. And then when we look at this aggregated heat metric that comes from combining this 99-degree statistic with other statistics, you see something that looks similar, but it's a little bit different. So obviously the Rocky Mountains are going to be low heat risk here, but just west of them, the aggregated heat metric is a little bit lower than in this 99-degree metric, and that's largely due to humidity effects. So this is just a drier part of the country, and so humans can sweat a little bit easier there, and heat risk is not quite as bad at a given temperature level. And the same thing is true in other regions of the world. So for example, comparing India and the UK, it is much hotter and humid, and that humidity effect will drive up the heat risk a little bit relative to drier places in the world like the Western US. So those are some of the choices that we have to step through to get to a final risk score. And they're not only coming from the climate modeling input, they're also coming from, well, how do we think about risk? What's important? And how do we interpret that for our particular use case? So let me stop there, Adriel, and ask if there are any questions or anything was unclear there that you want to cover a little bit more.
Yeah, thank you, Ed. Folks can chime in the chat or in the Q&A with questions. But just to go deeper on that, like India, UK example you just gave, I think that's a really interesting one. Because if you look at the maps inside of Beehive, India is all red because it's super, super hot. That makes perfect sense. And compared to India, the UK is not a very hot place. There's no way to change that. But two or three summers ago, I think it was summer 22, if you guys remember, there was a heat wave that hit London that caused directly and indirectly, I think 4,500 deaths in the UK. So a really, really serious, tragic, and business material heat wave hit the UK. But does that mean because it's not India, it should always be a low score and never a high score? Not really. So that's where you need to, or that's the decisions that we make, which is, do we compare the UK? How much do we compare the UK to India versus the UK to former versions of the UK, with a few variations there. So that's just an example of like how you guys on the business side might begin to think about, okay, I see a 7 out of 7 risk score in India and a 5 out of 7 risk score in the UK. Does that mean I shouldn't care at all about the UK? Well, maybe a 5 out of 7 in the UK is actually worse than a 7 in India, because in India they're used to sevens and they're used to 100-degree heat, whereas in the UK they are not. Is that kind of the right way of thinking about it, Ed?
Yeah, that's exactly right. And it goes back to one, probabilistic interpretation, and two, relative versus absolute risk, right? So we don't want to entirely ignore relative risk. We want to account for the fact that, a hot day might be very serious in London at a much lower temperature than India routinely gets. But on the other hand, if we go too far in that direction, then every location in the globe will have a 6 or a 7, and your risk score is effectively meaningless because there's just risk everywhere. So we try to balance some of that. And this is a great topic for feedback on what, how other people think of risk, what's useful, what's not useful, how should some of these choices be dialed in for customer thinking about risk and reporting, and that's one of the things we want to certainly talk more about with customers.
Yeah, another example there is the New York Times had a big story run last summer. I think they did an episode of the Daily about it, where some factories that were built in Indiana and parts of the U.S. Midwest, like 20 years ago, that were supposed to last 50 years, they were built assuming certain temperatures. And so they, that far north, were not built in with as good a ventilation or as good an air conditioning as you might have had further south. But all of a sudden, as these heat waves become more frequent and more intense, and just temperatures begin to rise, there's really, really high costs of operating those factories, because all of a sudden, when the temperature goes above a certain amount, OSHA says that you need to give your employees longer and more frequent breaks. Or if the temperature becomes unbearable and people literally can't work there, then you need to do a massive retrofit to install better ventilation and air conditioning. So those are examples where some of this modeling work is not necessarily about saying, I know that Indiana will be 6.5 degrees higher in 30 years than today, but it's looking at these scenarios and saying, what is my confidence level that there will be some amount of heat wave increase in this area or decrease? Maybe certain places are getting cooler. The whole, things vary. And then what decisions might you make? And then beginning to tie in a financial model for your own business to say, okay, I have a 30% confidence that heat waves will increase by 20%. And if that does happen, that'll cost me $20 million in retrofits. So let me decide if it's worth doing now or worth holding off a little bit, and waiting a little bit more. Folks are welcome to ask any questions. I've got one or two more for you, Ed. But talk a little bit about some of the trade-offs that we made. When we first started building these models, one of the thoughts was climate modeling is not new. Like you wrote in an earlier slide, it's been 60, 70 years since scientists have been doing some sort of long-term prediction. There are wonderful software companies that do an incredible job and have a huge financial war chest in trying to do like as accurate as possible climate modeling. They might say, not only we think this region, but this block or this building might have this level of change. And they might go deeper and say, we think this building has X level of risk because its roof is made out of Y material and it hasn't been changed in X number of years. And so therefore rain will impact this building more than its neighbor that is a more recent build. That is incredibly valuable to certain industries and certain customers. Very, very expensive to do, and certainly debatable about how accurate you can get. And so there's some perhaps value loss. But we actively decided to not do that, which is a trade-off. You're not going to get as detailed accuracy geographically and Beehive as you might through other softwares. We think it's a lot cheaper, and it'll be good enough information. But just talk a little bit about like that trade-off, that decision. maybe the benefits of one and what customers would lose by not having that level of detail.
Sure. Yeah, I think you set that up very well. It is a trade-off. So as you might expect, more resolution requires more resource investment. And th there are a lot of ways that you can add resolution to your model. A couple of examples are in wildfire models, it's typical to take satellite data that sort of exists at a much higher resolution than these climate data sets and overlay the satellite data indicating is this little pixel a forest, is this little pixel urban, is this little pixel a desert, and use that to sort of adjust your prediction one way or another. And we in fact do that with our wildfire modeling approach. You can do something similar with floods and elevation. So you can take a higher resolution data set of Earth's elevation, and this is data that's made available by the government, again, gathered through satellites, typically 30 meters resolution across the world. And you can do things like say, okay, well, I'm going to use that higher resolution flood data to create a much more resolved mesh of the Earth's surface. And then I'm going to go through and solve a set of equations on that more resolved mesh and get a better prediction or a more detailed prediction of where floodwaters are going to go in the event of extreme rainfall. And as you said, that costs a lot in a lot of cases. So it's not atypical to run a very large flooding simulation for a month or a couple of months on thousands of CPUs, and that's very expensive. And the question is, what's right for the use case? And what we've talked about internally is that there's a match here that we think is appropriate between the CMIP 6 kind of gold standard resolutions and climate modeling output and a class of companies that want to be compliant and want to get a good look at their risk without needing to go that extra step of paying a lot more for some of these really detailed finely resolved simulations. And so that's how we think about the balance and how we think about which kind of customer use case we want to solve for. And again, the trend in all of this is to go towards higher resolution modeling. So we are incorporating some of that elevation data, some of that more resolved wildfire data, excuse me, land cover data in our wildfire models, and we'll continue to do that. But at the same time, if we go the extra step of saying we're going to have 30-meter resolution for all of our models everywhere, that there's no way that's possible without adding a lot onto the cost of the product and the modeling. And so that's kind of the gist of the trade-off there.
Yeah. Um, and that works great for some. And for others, they're going to want, for example, somebody who this would not work well at all for is an agriculture company. Because if you have a huge farm growing tomatoes that only grow in this like 3-degree range, you really need to know, is it going to be 3.5 degrees more and in how many years? And what do you do with that? Do you move farms? Do you grow a new crop? Do you bring your food science to the tomato plant to make it more resilient? Like you got to be, and you need this on your 1,000-acre farm and don't get that wrong. So you will pay a lot of
Right,
money for immense accuracy,
right.
and
This is
that's
matching.
fantastic.
Yeah, that's right. And
Yeah,
if right. There are use cases for which the higher resolution is really required and very
yeah,
appropriate, and there are use cases for which it's not. And that's a matching exercise for sure.
yeah. I have one last question. I'll let folks chime in. Um, it's a little bit of a cheeky question, but this feels like the kind of thing you can type into ChatGPT and say, "Here's where my 12 offices are. Like, what is the risk to each office from wildfires?" This feels like so tailor-made for AI to understand complex models, to have this huge swath of data to read through and understand and turn into business language. Like, this feels so tailor-made for just some great AI model or be able to give you this information. What can AI do well? Like, what is good enough with AI? And where do you think it's still like the work that you're doing? A lot of it is not just, I mean, none of it is just typing into ChatGPT what's going to be the risk in all these places. Like, what can AI do very well right now, and where does it work well for a general user? And where is it still lacking? Like, what are we doing differently or better, or with our accuracy, or perhaps an audit trail that AI cannot do as well?
Yeah, yeah, that is a very interesting question. I'll step back just briefly and say, not only is AI being use case tested for the application you just mentioned of, okay, there's a lot of climate model data out there. How do I access that? How do I collate that and interpret it? AI is also being used to try and um, replace some of the traditional equation solving machinery that I mentioned as being at the core of these climate models. So there are papers recently in a couple of companies that are trying to replace the actual climate model itself with probably a transformer based AI stack that makes the sort of same weather predictions with the same resolution that a traditional weather model might. And there are efforts considered to do the same thing with the climate model itself. So there's an AI component of research within these models, but that's just something to be aware of. To answer your question, certainly you're going to get answers from the LLMs about is risk high or risk low if I ask about a location. They're designed to do that. They'll give you an answer, and that's going to work reasonable for a few locations and without providing a long chain of sourcing. And I think what we can add here with an approach like what Beehive is doing is one, having a systematic approach. In other words, if you asked an LLM for, tell me about the risk to my office in this state, and then tell me about the risk to my office in that state, and then also tell me about the risk in another country, the LLM might be using widely different data sources to get those risks, and you would never know about it. And so maybe it's not an apples to apples comparison. Additionally, we are with a systematic approach comes the ability to do this sort of audit trail work that you described, where we can talk a little bit about and show to a potential regulator, where do things come from? Why do we do this? Are we referencing gold standard CMIP6 data or not? Where does everything come from? That's a big benefit of this sort of an approach. And then finally, there's, I think, an ease of use argument in here about, well, if you want to do this at scale, the interactive prompt for querying your locations is going to get tedious at some point. So you either need to write something to automate that, and if you're doing it for many, many locations, then you're back at the problem of how is it going to be an apples to apples comparison about all across all these locations. And if you don't want to automate that, then it's just a very tedious exercise to by hand ask about every location. Maybe you want to upload a CSV and it can do it. But then again, you're going to need to compare risk types. It's just overhead associated with the analysis. And so what we're trying to do with this approach is to take a lot of the overhead out of that while keeping the systematic approach in place and the auditability in place. And that's where some of the benefit comes from versus just doing asset by asset entry in ChatGPT.
Perfect. Awesome. Thank you, Ed. All right. Thank you guys very much for joining today. I appreciate this. I hope this was interesting and valuable. Next week, Thursday, 2 p.m., every Thursday at 2 p.m. But next week, we're going to be talking about how to keep an employee safe during a wildfire. So what kind of program, standard operating procedure can you build as a plan? What should you do during the actual event? And then how can you help respond afterwards? So thank you, everyone, very much. Reach out anytime. And thank you, Ed. We'll see everyone soon.